One of the things we're dreaming about is to have some sort of series expansion involving Bessel functions. But before we can actually do that, we need to lay some groundwork, and that groundwork is Lommel's integral. So to start with, let's write down two very similar looking equations. So first of all, we have x squared d phi dx squared plus x d phi dx plus L squared x squared minus n squared phi equal to 0. And then we have a very similar looking equation involving psi. Okay, x d psi dx. And then rather than having an L here, we're going to have a k. So we have k squared x squared minus n squared psi equal to x. So these equations should look familiar. Pause the video and see if you can find out what their solutions are. So this looks very similar to Bessel's differential equation, right? Which was, if I just copy that again, we have x squared and then x prime plus x prime, and then we have x squared minus n squared x, that thing equal to 0. So you see, if we make a substitution here of the arguments, if we replace x by a scaled version, let's say a times x tilde, then if you do the substitution of variables, which is also something we did when we introduced the Bessel differential equation, you will notice that all of the factors that come from that substitution in these two terms cancel out. And the only thing that happens is that then the prefactor will appear here in this term x squared. So if you then compare all of these equations, then you will very easily see that the solutions are for phi, that it's the Bessel function of order n and of the argument Lx, and for psi it's Jn kx. So these are the solutions to those particular equations. Okay, now what Mr. Lommel was doing on some sort of rainy Sunday afternoon when he was bored is that he took the first equation and then he multiplied that equation by psi divided by x. And then he multiplied the second equation with minus phi divided by x. And then he added those two equations. So pause the video and see if you can reproduce that calculation. Okay, let's see what's happening. Let's first take a look at the two first terms of these two equations. So x squared will be divided by x, so we just have x, and then we have psi d2 phi dx squared minus phi d2 psi dx squared. Okay, that's good news, that's done. Then let's focus on these two terms here and combine them. So x divided by x, that just cancels out. And then we have psi d phi dx minus phi d psi dx. Okay, let's have a look at these guys here. So we have L squared, and then we have x squared divided by x, so that's going to be x. So we have L squared x phi psi. And here we have minus k squared x phi psi. So we can combine those to give us L squared minus k squared. And then we have x phi psi. And then finally, these two terms with n squared. So this will give us n squared divided by x phi psi. And here we have minus n squared divided by x phi psi. So these last contributions, they cancel. So this is the equation we have. So if you stare long and hard at this equation, you will notice that these first two terms, you can actually write them as a total differential, as d dx of some sort of function. So pause the video and see if you can figure out what that function is. It turns out you can actually write these first two terms as d dx of the product of x, and then that factor over here, psi d phi dx minus phi d psi dx. And then let's bring this thing over to the other side. K squared minus L squared x phi psi. If you weren't able to come up with this, you can also go the other way around and verify that taking the derivative of this thing indeed gives you these two terms. So if we take the derivative of the first factor, that's going to give us 1, and then we copy that second factor. That's what we find over here. And then we keep the first factor over there, and then we take the derivative of this thing between brackets here, and this will give us indeed this particular term, because all of the terms involving the product of the psi dx and the phi dx, they will cancel, and then you only get 2 terms out of 4 when you take the derivative of this final contribution here. Okay, so this seems like a bit of magic. So the reason this worked is because we exactly multiplied by these factors over here. If this thing seems to fall out of the sky, and indeed it does fall a bit out of the sky, but be aware of the fact that it is possible to derive what you should multiply these two equations with here, depending on the structure of that equation. So Lommel was not just lucky, he was looking at the structure of that equation to figure out how he could transform this thing into a total differential. Good. So now on the left-hand side, we have a total differential. And if you see something which is a total differential, that means you have the irresistible urge to take the integral of both sides, right? So let's do that now. Let's take the integral. And if we take the integral, then we get, so if we focus first on the right-hand side, we have k squared minus L squared, the integral of x phi psi. And let's again reintroduce what this phi and this psi were. So we have jn k of x, jn lx dx. And this thing is equal to, and then we just have the stuff between square brackets here. So this is going to give us x. And then for psi, we had jn k of x, as you can see here, jn kx. Okay, so jn kx, and then ddx of jn lx minus jn lx ddx jn kx. Okay, so that's the left-hand side after taking the integral. Plus, of course, an integration constant, but let's not bother about this thing here. So basically, we have calculated this integral here. The only thing we're doing now is just cosmetics, basically. So one thing we could do is, okay, we don't like this ddx because it takes up so much space. It would be much nicer to have a notation where we use prime in order to denote derivation. But there it's a little bit tricky, because if you write down something like jn prime of kx, what do we mean by that? Well, by definition, prime denotes derivation with respect to the total argument. So here, this is a shortcut for djn kx dkx. So we derive with respect to kx, not with respect to x. So if we use this definition of jn prime of kx, pause the video and rewrite this using that particular notation. So just using the chain rule here, you can write down that this is 1 over k djn kx dx. So if we need to replace djn kx dx, like terms we have here, that means that it can be replaced by the prime notation, but we multiply by that scaling factor over there. So if we do that, then we get for our integral, we have x, then we have jn kx, and then we have L jn prime Lx minus Jn Lx k Jn prime kx. Okay, plus our friend the integration constant. Again, this is just cosmetics, and let's take one more cosmetic step. Let's now say that you don't like the derivations, the derivatives after all, and you want to replace that by a Bessel function of a higher order. So let's say you want to move from Jn prime to, let's say, Jn plus 1. Can you do that? The issue is finding the right recurrence relationship. So pause the video, see if you can dig up a suitable recurrence relationship to do a final cosmetic transformation on this particular integral. So this is a promising recurrence relationship. We have Jn prime of x, and that's going to be equal to n over x Jn x minus Jn plus 1 x. So this is something we've derived earlier. Notice again that Jn prime of something denotes derivation with respect to the total argument, irrespective of what that total argument is called. It's a derivation with respect to x or t or k, or the tx or kx or any multiple of x. So what we can do here is we can replace x simply by L of x, and then everything will still keep on working, simply because by definition this is derivation with respect to the total argument. So we can call this argument whatever we want. And then of course we need the little friend here for k, and kx Jn kx minus Jn plus 1 kx. Okay, this seems like a useful thing to have, although it's a little bit scary because it seems that the price we pay for that is introducing some more terms. But if we take a look at what we have here, we have, for example, Jn prime Lx, but that gets multiplied by L. So if this thing gets multiplied by L, that means that we have this equation here also multiplied by L. That means that the L over here cancels. And then if you look at here, we need to multiply by Jn k of x. So with respect to this term, this will become n Jn L of x, Jn k of x. So the same thing will happen here, but then with k. But the upshot will be that for this particular term, after you multiply by k, you get exactly the same term as when you had this thing multiplied by L and multiplied with the non-derived function here. So the contribution from these two guys over here, that cancels. And the only thing we're left with is this particular term. So that tells us that we can replace the prime by a Bessel function of order n plus 1 without prime, and also by changing the sign. So these are the final things we need to do. And then we can write down the end result, and that is that if we have the integral of x Jn k of x Jn L of x dx. Now there used to be a factor L squared minus k squared, or k squared minus L squared here on the left hand side. So let's bring that over here. 1 over k squared minus L squared, which of course assumes that these guys are different. Otherwise we divide by 0. And then we substitute these guys into that thing. Since the sign flips and we have a minus sign here, we're first going to write down this thing. So that gives us finally k, and then Jn plus 1 kx, Jn Lx, and then minus L, and then we have Jn plus 1 Lx, Jn kx. And this is the most conventional form of Lommel's integral. This is going to be a useful result that we will build upon later to derive series expansions involving Bessel functions. So that's something to look forward to.